Chapter 3 Basic Instruments Introduction. Instruments mechanically measure physical quantities or properties with varying degrees of accuracy. Much of a navigator's work consists of applying corrections to the indications of various instruments and interpreting the results. Therefore, navigators must be familiar with the capabilities and limitations of the instruments available to them. A navigator obtains the following flight information from basic instruments: direction, altitude, temperature, airspeed, drift, and ground speed Gs. Some of the basic instruments are discussed in this chapter. The more complex instruments that make accurate and long-distance navigation possible are discussed in later chapters. Direction. Basic instruments. The navigator must have a fundamental background in navigation to ensure accurate positioning of the aircraft. Dead reckoning, doctor, procedures aided by basic instruments give the navigator the tools to solve the three basic problems of navigation: position of the aircraft, direction to destination, and time of arrival. Using only a basic instrument, such as the compass and drift information, you can navigate directly to any place in the world. Various fixing aids, such as celestial and radar, can greatly improve the accuracy of basic doctor procedures. This chapter discusses the basic instruments used for doctor and then reviews the mechanics of drive, plotting, wind effect, and computer solutions. Directional information needed to navigate is obtained by use of the Earth's magnetic lines of force. A compass system uses a device that detects and converts the energy from these lines of force to an indicator reading. The magnetic compass operates independently of the aircraft electrical systems. Later developed compass systems require electrical power to convert these lines of force to an aircraft heading. Earth's magnetic field. The Earth has some of the properties of a bar magnet, however, its magnetic poles are not located at the geographic poles, nor are the two magnetic poles located exactly opposite each other as on a straight bar. The North Magnetic Pole is located approximately at 73 degrees north latitude and 100 degrees west longitude on Prince of Wales Island. The South Magnetic Pole is located at 68 degrees south latitude and 144 degrees east longitude on Antarctica. The Earth's magnetic poles, like those of any magnet, can be considered to be connected by a number of lines of force. These lines result from the magnetic field that envelops the Earth. Earth's magnetic field. They are considered to be emanating from the South Magnetic Pole and terminating at the North Magnetic Pole. Figure 3.1. The force of the magnetic field of the Earth can be divided into two components, the vertical and the horizontal. The relative intensity of these two components varies over the Earth so that, at the magnetic poles, the vertical component is at maximum strength and the horizontal component is minimum strength. At approximately the midpoint between the poles, the horizontal component is at maximum strength and the vertical component is at minimum strength. Only the horizontal component is used as a directive force for a magnetic compass. Therefore, a magnetic compass loses its usefulness in an area of weak horizontal force, such as the area around the magnetic poles. The vertical component causes the end of the needle nearer to the magnetic pole to tip as the pole is approached. Figure 3.1. This departure from the horizontal is called magnetic dip. Compasses. A compass may be defined as an instrument that indicates direction over the Earth's surface with reference to a known datum. Various types of compasses have been developed, each of which is distinguished by the particular datum used as the reference from which direction is measured. Two basic types of compasses are in current use, the magnetic and gyro compass. The magnetic compass uses the lines of force of the Earth's magnetic field as a primary reference. Even though the Earth's field is usually distorted by the pressure of other local magnetic fields, it is the most widely used directional reference. The gyro compass uses as its datum an arbitrary fixed point in space determined by the initial alignment of the gyroscope axis. Compasses of this type are widely used today and may eventually replace the magnetic compass entirely. Magnetic compass. The magnetic compass indicates direction in the horizontal plane with reference to the horizontal component of the Earth's magnetic field. This field is made up of the Earth's field in combination with other magnetic fields in the vicinity of the compass. These secondary fields are caused by the presence of ferromagnetic objects. Magnetic compasses may be divided into two classes. 1. The direct indicating magnetic compass, in which the measurement of direction is made by a direct observation of the position of a pivoted magnetic needle, and 2. The remote indicating gyro-stabilized magnetic compass. Magnetic direction is sensed by an element located at positions where local magnetic fields are at a minimum, the Earth's magnetic field compared to a bar magnet, such as the vertical stabilizer and wingtips. The direction is then transmitted electrically to repeater indicators on the instrument panels. Direct indicating magnetic compass. Basically, the magnetic compass is a magnetized rod pivoted at its middle, with several features incorporated to improve its performance. One type of direct indicating magnetic compass, the B16 compass, often called the whiskey compass, is illustrated in Figure 3.2. It is used as a standby compass in case of failure of the electrical system that operates the remote compasses. It is a reliable compass and gives good navigational results if used carefully. Magnetic variation and compass errors. The Earth's magnetic poles are joined by irregular curves called magnetic meridians. The angle between the magnetic meridian and the geographic meridian is called the magnetic variation. Variation is listed on charts as east or west. When variation is east, magnetic north, Mn, is east of true north, Tn. Similarly, when variation is west, Mn is west of Tn. Figure 3.3, lines connecting points having the same magnetic variation are called isogonic lines. Figure 3.4, compensate for magnetic variation to convert a compass direction to true direction. Compass error is caused by nearby magnetic influences, such as magnetic material in the structure of the aircraft and its electrical systems. These magnetic forces deflect a compass needle from its normal alignment. The amount of such deflection is called deviation, which, like variation, is labeled east or west as the north-seeking end of the compass is deflected east or west of Mn, respectively. The correction for variation and deviation is usually expressed as a plus or minus value and is computed as a correction to true heading Th. If variation or deviation is east, the sign of the correction is minus; if west, the sign is plus. A rule of thumb for this correction is easily remembered as east is least and west is best. Aircraft headings are expressed as Th or magnetic headings, Mh. If the heading is measured in relation to geographical north, it is a Th. If the heading is in reference to Mn, it is a Mh. If it is in reference to the compass lubber line, it is a compass heading, Ch. Ch corrected for variation and deviation is Th. Mh corrected for variation is Th. This relationship is best expressed by reference to the navigator's log, where the various headings and corrections are listed as Th, variation var, Mh, deviation dev and Ch. Figure 3.5, thus, if an aircraft is flying in an area where the variation is 10 degrees east and the compass has a deviation of 3 degrees east, the relationship would be expressed as follows, assuming a Ch of 125 degrees, Th var Mh dev Ch 138 to 10 equals 128 to 3 equals 125. Variation has been measured throughout the world and the values found have been plotted on charts. Isogonic lines are printed on most charts used in aerial navigation so that, if the aircraft's approximate position is known, the amount of variation can be determined by visual interpolation between the printed lines. At high altitudes, these values can be considered quite realistic. Conversely, at low altitudes, these magnetic values are less reliable because of local anomalies. Variation changes slowly over a period of years and the yearly amount of such change is printed on most charts. Variation is also subject to small diurnal daily changes that may generally be neglected in air navigation. Deviation. Because deviation depends upon the distribution of magnetic forces in the aircraft itself, it must be obtained individually for each magnetic compass on each aircraft. The process of determining deviation, known as compass swinging, should be discussed in the technical order for each compass. Deviation changes with heading are shown in Figure 3.6. The net result of all magnetic forces of the aircraft, those forces excluding the Earth's field, is represented by a dot located just behind the wings of the aircraft. If the aircraft is headed toward Mn, the dot attracts one pole of the magnetic compass, in this case, the south pole, but, on this heading, does not change its direction. The only effect is to amplify the directive force of the Earth's field. If the aircraft heads toward magnetic east, the dot is now west of the compass, and attracts the south pole of the compass, causing easterly deviation. Figure 3.6 also shows that the deviation is 0 on a south heading, and westerly when the aircraft is heading west. Deviation can be reduced, but not eliminated, in some direct indicating magnetic compasses by adjusting the small compensating magnets in the compass case. Remaining deviation is referred to as residual deviation and can be determined by comparison with true values. This residual deviation is recorded on a compass correction card showing actual deviation on various headings or the compass headings. From the compass correction card illustrated in Figure 3.7, the navigator knows that to fly a magnetic heading, MH, of 270 degrees, the pilot must steer a CH of 268 degrees. Errors in flight. Unfortunately, deviation is not the only error of a magnetic compass. Additional errors are introduced by the motion of the aircraft itself. These errors have minimal effect on the use of magnetic compasses and come into play normally during turns or changes in speed. They are mentioned only to bring awareness of the limitations of the basic compass. Although a basic magnetic compass has some shortcomings, it is simple and reliable. The compass is very useful to both the pilot and navigator and is carried on all aircraft as an auxiliary compass. Because compass systems are dependent upon the electrical system of the aircraft, A loss of power means a loss of the compass system. For this reason, an occasional check on the standby compass provides an excellent backup to the main systems. Remote indicating gyro-stabilized magnetic compass system. A chief disadvantage of the simple magnetic compass is its susceptibility to deviation. In remote indicating gyro-stabilized compass systems, this difficulty is overcome by locating the compass direction sensing device outside magnetic fields created by electrical circuits in the aircraft. This is done by installing the direction sensing device in a remote part of the aircraft, such as the outer extremity of a wing or vertical stabilizer. Indicators of the compass system can then be located throughout the aircraft without regard to magnetic disturbances. Several kinds of compass system are used in aircraft systems. All include the following 5 basic components: remote compass transmitter, directional gyro, DG, amplifier, heading indicators, and slaving control. Though the names of these components vary among systems, the principle of operation is identical for each. Thus, the N1 compass system shown in Figure 3.8 can be considered typical of all such systems. The N1 compass system is designed for airborne use at all latitudes. It can be used either as a magnetic slaved compass or as a DG. In addition, the N1 generates an electric signal that is used as an azimuth reference by the autopilot, the radar system, the navigation and bombing computers, and various compass cards. Remote compass transmitter. The remote compass transmitter is the magnetic direction sensing component of the compass system when the system is in operation as a magnetic slaved compass. The transmitter is located as far from magnetic disturbances of the aircraft as possible, usually in a wingtip or the vertical stabilizer. The transmitter senses the horizontal component of the Earth's magnetic field and electrically transmits it to the master indicator. The compensator, an auxiliary unit of the remote compass transmitter, is used to eliminate most of the magnetic deviation caused by the aircraft electrical equipment and ferrous metal when a deviation-free location for the remote compass transmitter is not available. Directional gyro, DG. The DG is the stabilizing component of the compass system when the system is in magnetic slaved operation. When the compass system is in DG operation, the gyro acts as the directional reference component of the system. Amplifier. The amplifier is the receiving and distributing center of the compass system. Azimuth correction and leveling signals originating in the components of the system are each received, amplified, and transmitted by separate channels in the amplifier. Primary power to operate the compass is fed to the amplifier and distributed to the system's components. Master indicator. The master indicator is the heading indicating component of the compass system. The mechanism in the master indicator integrates all data received from the directional gyro and the remote compass transmitter, corrects the master indicator heading pointer for azimuth drift of the DG due to the Earth's rotation, and provides takeoff signals for operating remote indicators, radar, navigation computers, and directional control of the autopilot. The latitude correction control provides a means for selecting either magnetic slaved operation or DG operation of the compass system, as well as the proper latitude correction rate. The latitude correction pointer is mechanically connected to the latitude correction control knob and indicates the latitude setting on the latitude correction scale at the center of the master indicator dial face. The synchronizer control knob at the lower right-hand corner of the master indicator face provides a means of synchronizing the master indicator heading pointer with the correct MH when the system is in magnetic slaved operation. It also provides a means of setting the master indicator heading pointer on the desired gyro heading reference when the system is in DG operation. The annunciator pointer indicates the direction in which to rotate the synchronizer control knob to align the heading pointer with the correct MH. Gyromagnetic compass indicators. The gyromagnetic compass indicators are remote reading, movable dial compass indicators. They are intended for supplementary use as directional compass indicators when used with the compass system. The indicators duplicate the azimuth heading of the master indicator heading pointer. A setting knob is provided at the front of each indicator for rotating the dial 360 degrees in either direction without changing the physical alignment of the pointer. Slaving control. The slaving control is a gyro control rate switch that reduces errors in the compass system during turns. When the aircraft turns at a rate of 23 degrees or more per minute, the slaving control prevents the remote compass transmitter signal from being transmitted to the compass system during magnetic slaved operation. It also interrupts leveling action in the DG when the system is in magnetic slaved or DG operation. Gyro basics. Any spinning body exhibits gyroscopic properties. A wheel designed and mounted to use these properties is called a gyroscope or gyro. Basically, a gyro is a rapidly rotating mass that is free to move about one or both axes perpendicular to the axis of rotation and to each other. The three axes of a gyro, spin, drift, and topple, shown in Figure 3.9 are defined as follows. 1. In a DG, the spin axis or axis of rotation is mounted horizontally. 2. The topple axis is that axis in the horizontal plane that is 90 degrees from the spin axis. 3. The drift axis is that axis 90 degrees vertically from the spin axis. Gyroscopic drift is the horizontal rotation of the spin axis about the drift axis. Topple is the vertical rotating of the spin axis about the topple axis. These two component drifts result in motion of the gyro called precession. A freely spinning gyro tends to maintain its axis in a constant direction in space, a property known as rigidity in space or gyroscopic inertia. Thus, if the spin axis of a gyro were pointed toward a star, it would keep pointing at the star. Actually, the gyro does not move, but the Earth moving beneath it gives it an apparent motion. This apparent motion is called apparent precession. Figure 3.10, the magnitude of apparent precession is dependent upon latitude. The horizontal component, drift, is equal to 15 degrees per hour times the sine of the latitude, and the vertical component, topple, is equal to 15 degrees per hour times the cosine of the latitude. These computations assume the gyro is stationary with respect to the Earth. If the gyro is to be used in a high-speed aircraft, however, it is readily apparent that its speed with respect to a point in space may be more or less than the speed of rotation of the Earth. If the aircraft in which the gyro is mounted is moving in the same direction as the Earth, the speed of the gyro with respect to space is greater than the Earth's speed. The opposite is true if the aircraft is flying in a direction opposite to that of the Earth's rotation. This difference in the magnitude of apparent precession caused by transporting the gyro over the Earth is called transport precession. A gyro may precess because of factors other than the Earth's rotation. When this occurs, the precession is labeled real precession. When a force is applied to the plane of rotation of a gyro, the plane tends to rotate, not in the direction of the applied force, but 90 degrees around the spin axis from it. This torquing action, shown in Figure 3.11, may be used to control the gyro by bringing about a desired reorientation of the spin axis, and most DGs are equipped with some sort of device to introduce this force. However, friction within the bearings of a gyro may have the same effect and cause a certain amount of unwanted precession. Great care is taken in the manufacture and maintenance of gyroscopes to eliminate this factor as much as possible, but, as yet, it has not been possible to eliminate it entirely. Precession caused by the mechanical limitations of the gyro is called real or induced precession. The combined effects of apparent precession, transport precession, and real precession produce the total precession of the gyro. The properties of the gyro that most concern the navigator are rigidity and precession. By understanding these two properties, the navigator is well equipped to use the gyro as a reliable steering guide. Directional gyro, DG, the discussion thus far has been of a universally mounted gyro, free to turn in the horizontal or vertical or any component of these two. This type of gyro is seldom, if ever, used as a DG. When the gyro is used as a steering instrument, it is restricted so that the spin axis remains parallel to the surface of the Earth. Thus, the spin axis is free to turn only in the horizontal plane, assuming the aircraft normally flies in a near-level attitude, and only the horizontal component, drift, affects a steering gyro. In the terminology of gyro steering, precession always means the horizontal component of precession. The operation of the instrument depends upon the principle of rigidity in space of the gyroscope. Fixed to the plane of the spin axis is a circular compass card, similar to that of the magnetic compass. Since the spin axis remains rigid in space, the points on the card hold the same position in space relative to the horizontal plane. The case, to which the lubber line is attached, simply revolves about the card. It is important at this point to understand that the numbers on the compass card have no meaning within themselves, as on the magnetic compass. The fact that the gyro may indicate 100 degrees under the lubber line is not an indication that the instrument is actually oriented to magnetic north, MN, or any other known point. To steer by the gyro, the navigator must first set it to a known direction or point. Usually, this is MN or geographic north, though it can be at any known point. If, for example, MN is set as the reference, all headings on the gyro read relative to the position of the magnetic poles. The actual setting of the initial reference heading is done by using the principle discussed earlier of torque application to the spinning gyro. By artificially introducing precession, the navigator can set the gyro to whatever heading is desired and can reset it at any time, by using the same technique. Gyro compass error is the major error affecting the gyro, and its use as a steering instrument is precession. Apparent precession causes an apparent change of heading equal to 15 degrees per hour times the sine of the latitude. Real precession, caused by defects in the gyro, may occur at any rate, but is typically very small in current gyros. Apparent precession is a known value depending upon location and can be compensated for. In some of the more complex gyro systems, apparent precession is compensated for by setting in a constant correction equal to, and in the opposite direction to, the precession caused by the Earth's rotation. Altitude and altimeters. Altitude may be defined as a vertical distance above some point or plane used as a reference. Knowledge of the aircraft altitude is imperative for terrain clearance, aircraft separation, and a multitude of operational reasons. There are as many kinds of altitude as there are reference planes from which to measure them. Only 6 concern the navigator: indicated altitude, calibrated altitude, pressure altitude, PA, density altitude, DA, true altitude, TA, and absolute altitude. There are 2 main types of altimeters: the pressure altimeter, which is installed in every aircraft, and the absolute or radar altimeter. To understand the pressure altimeter's principle of operation, a knowledge of the standard datum plane is essential. Standard datum plane. The standard datum plane is a theoretical plane where the atmospheric pressure is 29.92 inches of mercury, Hg, and the temperature is 15 degrees Celsius. The standard datum plane is the zero elevation level of an imaginary atmosphere known as the standard atmosphere. In the standard atmosphere, pressure is 29.92 Hg at 0 feet and decreases upward at the standard pressure lapse rate. The temperature is 15 degrees Celsius at 0 feet and decreases at the standard temperature lapse rate. Both the pressure and temperature lapse rates are given in Figure 3.12. The standard atmosphere is theoretical. It was derived by averaging the readings taken over a period of many years. The list of altitudes and their corresponding values of temperature and pressure given in the table were determined by these averages. The height of the aircraft above the standard datum plane, 29.92 Hg and 15 degrees Celsius, is the PA. Figure 3.13. Pressure altimeter. Principles of operation. The pressure altimeter is an aneroid barometer calibrated to indicate feet of altitude instead of pressure. As shown in Figure 3.14, the pointers are connected by a mechanical linkage to a set of aneroid cells. These aneroid cells expand or contract with changes in barometric pressure. In this manner, the cells assume a particular thickness at a given pressure level and thereby position the altitude pointers accordingly. On the face of the altimeter is a barometric scale that indicates the barometric pressure, expressed in inches of mercury, of the point or plane from which the instrument is measuring altitude. Turning the barometric pressure set knob on the altimeter manually changes this altimeter setting on the barometric scale and results in simultaneous movement of the altitude pointers to the corresponding altitude reading. Like all measurements, an altitude reading is meaningless if the point from which it starts is unknown. The face of the pressure altimeter supplies both values. The position of the pointers indicates the altitude in feet, and the barometric pressure appearing on the barometric scale is that of the reference plane above which the measurement is made. Altimeter displays counterpointer altimeter. The counterpointer altimeter has a 2-counter digital display unit located in the 9 o'clock position of the dial. The counter indicates altitude in 1,000-foot increments from 0 to 80,000 feet. Figure 3.15, a single conventional pointer indicates LOOS of feet on the fixed circular scale. It makes 1 complete revolution per 1,000 feet of altitude change and, as it passes through the 900 to 1,000 foot area of the dial. The 1,000 foot counter is actuated. The shaft of the 1,000 foot counter in turn actuates the 10,000 foot counter at each 10,000 feet of altitude change. To determine the indicated altitude, first read the 1,000 foot counter and then add the 100 foot pointer indication. It is possible to misinterpret the counterpointer altimeter by 1,000 feet immediately before or after the 1,000 foot counter moves. This error is possible because the 1,000 foot counter changes when the 100 foot pointer is between the 900 and 1,000 foot position. Counter drum pointer altimeter. Aside from the familiar circular scale and 100 foot pointer, the counter drum pointer presentation differs somewhat in appearance from the present 3-pointer altimeter. Starting at the left of the instrument illustrated in Figure 3.16 and reading from left to right, there are 2 counter windows and 1 drum window, white. The numerals presented in the counter windows indicate 10,000s and 1,000s of feet, respectively. The drum window numbers always follow the pointer number, thereby indicating 100s of feet. 2 methods may be used to read indicated pressure altitude on the counter drum pointer altimeter. 1. Read the counter drum window, without referring to the 100 foot pointer, as a direct digital readout of both thousands and hundreds of feet. 2. Read the 2 counter indications, without referring to the drum, and then add the 100 foot pointer indication. The 100 foot pointer serves as a precise readout of values less than 100 feet. The differential air pressure that is used to operate the counter drum pointer altimeter is processed by an altitude transducer where it is converted to electrical signals that drive the indicator. The transducer is also used to send digital signals to a transponder for purposes of automatic altitude reporting to Air Route Traffic Control Centers, ARC. A standby system is available for use if an electrical malfunction occurs. In the standby system, The altimeter receives static air pressure directly from the pitot-static system. When the instrument is operating in the standby system, the word standby appears on the instrument face. A switch in the upper right-hand corner of the instrument is provided to return the instrument to its normal mode of operation. This switch may also be used to manually place the instrument in the standby mode. Altimeter errors. The pressure altimeter is subject to certain errors that fall in 5 general categories. Mechanical error. A mechanical error is caused by misalignment of gears and levers that transmit the aneroid cell expansion and contraction to the pointers of the altimeter. This error is not constant and must be checked before each flight by the setting procedure. Scale error. A scale error is caused by irregular expansion of the aneroid cells and is recorded on a scale correction card maintained for each altimeter in the instrument maintenance shop. Installation or position error. An installation, or position, error is caused by the airflow around the static ports. This error varies with the type of aircraft, airspeed, and altitude. The magnitude and direction of this error can be determined by referring to the performance data section in the aircraft technical order. An altimeter correction card is installed in some aircraft that combines the installation or position and scale errors. The card indicates the amount of correction required at different altitudes and airspeeds. Installation, or position, error may be considerable at high speeds and altitudes. Apply the corrections as outlined in the technical order or on the altimeter correction card. Reversal error. A reversal error is caused by inducing false static pressure in the static system. It normally occurs during abrupt or large pitch changes. This error appears on the altimeter as a momentary indication in the opposite direction. Hysteresis error. A hysteresis error is a lag in altitude indication caused by the elastic properties of the material within the altimeter. This occurs after an aircraft has maintained a constant altitude for an extended period of time and then makes a large, rapid altitude change. After a rapid descent, altimeter indications are higher than actual. This error is negligible during climbs and descents at slow rate or after maintaining a new altitude for a short period of time. Setting the altimeter. The barometric scale is used to set a reference plane into the altimeter. Rotating the barometric pressure set knob increases or decreases the scale reading and the indicated altitude. Each 0.01 change on the barometric scale is equal to 10 feet of altitude. The majority of altimeters have mechanical stops at or just beyond the barometric scale limits, 28.10 to 31.00. Attempting to adjust outside this range may cause damage to the instrument. Altimeters not equipped with mechanical stops near the barometric scale limits can be set with a 10,000-foot error. Therefore, when setting the altimeter, ensure the 10,000-foot pointer is reading correctly. Check the altimeter for accuracy before every flight. To check and set the altimeter, 1. Set the current altimeter setting on the barometric scale. 2. Check the altimeter at a known elevation and note the error in feet. 3. Set the reported altimeter setting on the barometric scale and compare the indicated altitude to the elevation of a known cockpit. Non-standard atmospheric effects. The altimeter setting is a correction for non-standard surface pressure only. Atmospheric pressure is measured at each station and the value obtained is corrected to sea level according to the surveyed field elevation. Thus, the altimeter setting is the computed sea level pressure and should be considered valid only in close proximity to the station and the surface. It does not reflect non-standard temperature nor distortion of atmospheric pressure at higher altitudes. Types of altitude. Indicated altitude. Indicated altitude is the value of altitude that is displayed on the pressure altimeter. Calibrated altitude. Calibrated altitude is indicated altitude corrected for installation or position error. Pressure altitude, PA, the height above the standard datum plane, 29.92 Hg and 15 degrees Celsius, is PA. Figure 3.13, density altitude, DA, density is mass per unit volume. The density of the air varies with temperature and with height. Warm air expands and is less dense than cold air. Normally, the higher the PA, the less dense the air becomes. The density of the air can be expressed in terms of the standard atmosphere. dA is the PA corrected for temperature in the density altitude window of the Doppler computer. This calculation converts the density of the air to the standard atmospheric altitude having the same density. dA is used in performance data and true airspeed, TAS, calculations. True altitude, TA is the actual vertical distance above mean sea level, MSL, measured in feet. It can be determined by 2 methods. 1. Set the local altimeter setting on the barometric scale of the pressure altimeter to obtain the indicated true altitude, ITA. The eta can then be resolved to TA by use of the Doppler computer. Figure 3.17.2. Measure altitude over water with an absolute altimeter. The height above the terrain is called absolute altitude. It is computed by subtracting terrain elevation from TA, or it can be read directly from a radar altimeter. The two altitudes most commonly accomplished on the computer are TA and DA. Nearly all doctor computers have a window by which DA can be determined, however, be certain that the window is labeled density altitude. True altitude, TA, determination in the space marked for altitude computations are two scales, a centigrade scale in the window and a PA scale on the upper disk. When a PA is placed opposite the temperature at that height, all values on the outer miles scale are equal to the corresponding values on the inner minutes scale, increased or decreased by 2% for each 5.5 degrees Celsius that the actual temperature differs from the standard temperature at that PA, as set in the window. Although the PA is set in the window, the eta is used on the inner minutes scale for finding the TA, corrected for difference in temperature lapse rate. PA equals 8,500 feet, eta equals 8,000 feet, air temperature equals minus 16 degrees Celsius. Place PA, 8,500 feet, opposite the temperature, minus 16, on the for altitude computation scale. Opposite the eta, 8,000 feet, on the inner scale, read the TA, 7,600 feet, on the outer scale. Figure 3L7, density altitude, DA, determination. DA determination on the computer is accomplished by using the window just above for airspeed and density altitude computations and the small window just above that marked density altitude. PA equals 9,000 feet, air temperature equals 10 degrees Celsius. Place pressure altitude, 9,000 feet, opposite air temperature, 10, in window marked for airspeed and density altitude, read DA, 10,400 feet. Figure 318. Absolute altimeter. Accurate absolute altitude is an important requisite for navigation, as well as for safe aviating. It is particularly important in pressure pattern navigation. Absolute altitude may be computed from the PA readings if the position of the aircraft is known, but the results are often inaccurate. Under changing atmospheric conditions, corrections applied to PA readings to obtain TAs are only approximate. In addition, any error made in determining the terrain elevations results in a corresponding error in the absolute altitude. Radar altimeter high level. A typical high-level radar altimeter is designed to indicate absolute altitude of the aircraft up to 50,000 feet above the terrain, land, or water. This altimeter does not warn of approaching obstructions, such as mountains, because it measures altitude only to a point directly below the aircraft. Figure 319. A typical set consists of the radar receiver transmitter, height indicator, and antenna. The transmitter section of the receiver transmitter unit develops recurring pulses of radio frequency, RF, energy that are delivered to the transmitter antenna located either flush mounted or on the underside of the aircraft. The transmitter antenna radiates the pulsed energy downward to reflect off the earth and return to the receiver antenna on the aircraft. The time consumed between transmission and reception of the RF pulse is determined only by the absolute altitude of the aircraft above the terrain, since the radio wave velocity is constant. The receiver antenna delivers the returned pulse to the receiver section of the receiver transmitter unit, where it is amplified and detected for presentation on the indicator unit. The radar altimeter indicator displays absolute altitude, which is used in pressure pattern navigation, terrain clearance, or as a backup for the PA. This type altimeter provides a dial or digital indication of the altitude of the aircraft above the terrain. It is designed to eliminate the necessity of adding antennas or any other equipment external to the surface of the aircraft. This equipment may also be used in conjunction with automatic pilot or other devices requiring altitude limit data. Figure 320, systems vary widely, but typically include a receiver transmitter, height indicator, and electronic control amplifier. The height indicator contains the only operating control on the equipment. This instrument normally gives altitude readings up to 35,000 feet. If the instrument has an analog scale, the markings are usually logarithmic, graduated for the low altitude portion of its range. A variable altitude limit indicator system is included to provide an indication of flight below a preset altitude. To operate the equipment, turn the on-limit control to on. After warm-up, the terrain clearance of the aircraft within the range of 0 to 20,000 is read directly from the single pointer on the indicator. Figure 320, this pointer can be preset to any desired altitude by the on-limit control and is used as a reference for flying at fixed altitudes. The altitude can be maintained by observing the position of the pointer with respect to the small triangular marker instead of the actual altitude scale. In addition, a red light on the front of the indicator lights up when the aircraft is at or below the preset altitude. To turn off the equipment, it is only necessary to turn off the on-limit control on the indicator. Temperature determination of correct temperature is necessary for accurate computation of airspeed and altitude. Temperature, airspeed, and altitude are all closely interrelated, and the navigator must be familiar with each in order to work effectively and accurately. Temperature gauge is the temperature gauge that is most commonly used in aircraft employs a bimetallic element. The instrument is a single unit consisting of a stainless steel stem that projects into the airstream and a head that contains the pointer and scale. The sensitive element in the outside end of the stem is covered by a radiation shield of brightly polished metal to cut down the amount of heat that the element might absorb by direct radiation from the sun. The bimetallic element, called the sensitive element, is so named because it consists of two strips of different metal alloys welded together. When the element is heated, one alloy expands more rapidly than the other, causing this element, which is shaped like a coil spring, to turn. This, in turn, causes the indicator needle to move on the pointer dial. Temperatures between -60 degrees Celsius and +50 degrees Celsius can be measured on this type of gauge. Temperature scales in the United States, temperature is usually expressed in terms of the Fahrenheit scale, degree Fahrenheit. In aviation, temperature is customarily measured on the centigrade, or Celsius, degree Celsius scale. Although aircraft thermometers are usually calibrated in degrees Celsius, it is sometimes necessary to interconvert Fahrenheit and centigrade temperatures. The following formulas may be used: degree Fahrenheit equals 1.8 times degree Celsius, plus 32 degrees Celsius equals degree Fahrenheit, 32 degrees, divided by 1.8. Temperature error is the total effect of scale error and heat of compression error. Scale error is simply an erroneous reading of the pointer under standard conditions. It is difficult for a crew member to evaluate this error without sensitive testing equipment. With this in mind, the reading of the indicator is considered correct and is called indicated air temperature, IAT. The second error, heat of compression error, causes the instrument to read too warm. Heating occurs at high speeds from friction and the compression of air on the forward edge of the temperature probe. Thus, the IAT is always corrected by a minus correction factor to produce true air temperature, TAT. Heat of compression increases with TAS. The TAT can be obtained from the aircraft flight manual. Airspeed is the speed of the aircraft in relation to the air mass surrounding that aircraft. Pitot-static system accurate airspeed measurement is obtained by means of a pitot-static system. The system consists of 1. A tube mounted parallel to the longitudinal axis of the aircraft in an area that is free of turbulent air generated by the aircraft, and 2. A static source that provides still, or undisturbed, air pressure. Ram and static pressures may be taken from a single pitot-static tube or from completely separate sources. A pitot-static tube usually has a baffle plate, figure 321, to reduce turbulence and to prevent rain, ice, and dirt from entering the tube. There may be one or more drain holes in the bottom of the tube to dispose of condensed moisture. A built-in electrical heating element, controlled by a switch inside the aircraft, prevents the formation of ice in the tube. Reasonable care should be taken with the pitot-static system to ensure continuous, reliable service. The drain holes should be checked periodically to ensure they are not clogged. At the completion of each flight, a cover is placed over the intake end of the tube to prevent foreign objects and moisture from collecting in the tube. Principles of operation of airspeed indicators. The heart of the airspeed indicator is a diaphragm that is sensitive to pressure changes. Figure 321 shows it located inside the indicator case and connected to the ram air source in the pitot tube. The indicator case is sealed airtight and connected to the static pressure source. The differential pressure created by the relative effects of the impact and static pressures on the diaphragm causes it to expand or contract. As the speed of the aircraft increases, the impact pressure increases, causing the diaphragm to expand. Through mechanical linkage, the expansion is displayed as an increase in airspeed. This principle is used in the EAS meter, the TAS meter, and the Mach meter. Airspeed definitions. There are many reasons for the difference between EAS and TAS. Some of the reasons are the error in the mechanical makeup of the instrument, the error caused by incorrect installation, and the fact that density and pressure of the atmosphere vary from standard conditions. Indicated airspeed, IAS, EAS is the uncorrected reading taken from the face of the indicator. It is the airspeed that the instrument shows on the dial. Basic airspeed, BAS, basic airspeed, BAS, is the EAS corrected for instrument error. Each airspeed indicator has its own characteristics that cause it to differ from any other airspeed indicator. These differences may be caused by slightly different hairspring tensions, flexibility of the diaphragm, accuracy of the scale markings, or even the effect of temperature on the different metals in the indicator mechanism. The effect of temperature introduces an instrument error due to the variance in the coefficient of expansion of the different metals comprising the working mechanisms. This error can be removed by the installation of a bimetallic compensator within the mechanical linkage. This bimetallic compensator is installed and properly set at the factory, thereby eliminating the temperature error within the instrument. The accuracy of the airspeed indicator is also affected by the length and curvature of the pressure line from the pitot tube. These installation errors must be corrected mathematically. Installation, scale, and instrument errors are all combined under one title called instrument error. Instrument error is factory determined to be within specified tolerances for various airspeeds. It is considered negligible or is accounted for in technical order tables and graphs. Calibrated airspeed, CAS, calibrated airspeed, CAS, is basic airspeed corrected for pitot-static error or attitude of the aircraft. The pitot-static system of a moving aircraft has some error. Minor errors are found in the pitot section of the system. The major difficulty is encountered in the static pressure section. As the flight attitude of the aircraft changes, the pressure at the static inlets changes. This is caused by the airstream striking the inlet at an angle. Different types and locations of installations cause different errors. It is immaterial whether the status source is located in the pitot-static head or at some flush mounting on the aircraft. This error is essentially the same for all aircraft of the same model, and a correction can be computed by referring to tables in the appendix of the flight manual. Equivalent airspeed, EAS, equivalent airspeed, EAS, is CAS corrected for compressibility. Compressibility becomes noticeable when the airspeed is great enough to create an impact pressure that causes the air molecules to be compressed within the impact chamber of the pitot tube. The amount of the compression is directly proportionate to the impact pressure. As the air is compressed, it causes the dynamic pressure to be greater than it should be. Therefore, the correction is a negative value. The correction for compressibility error can be determined by referring to the performance data section of the aircraft flight manual or by using the F correction factor on the doctor computer. Density airspeed, DAS, density airspeed, DAS, is calibrated airspeed corrected for PA and TAT. Pitot pressure varies not only with airspeed but also with air density. As the density of the atmosphere decreases with height, pitot pressure for a given airspeed must also decrease with height. Thus, an airspeed indicator operating in a less dense medium than that for which it was calibrated indicates an airspeed lower than true speed. The higher the altitude, the greater the discrepancy. The necessary correction can be found on the doctor computer. Using the window on the computer above the area marked for airspeed density altitude computations, set the PA against the TAT. Opposite the CAS on the minutes scale, read the DAS on the miles scale. At lower airspeeds and altitudes, DAS may be taken as true airspeed with negligible error. However, at high speeds and altitudes, this is no longer true and compressibility error must be considered. Compressibility error is explained in the equivalent airspeed section. When dA is multiplied by the compressibility factor, the result is true airspeed. True airspeed, TAS, is equivalent airspeed that has been corrected for air density error. By correcting E's for TAT and PA, the navigator compensates for air density error and computes an accurate value of TAS. The TAS increases with altitude when the ES remains constant. When the TAS remains constant, the ES decreases with altitude. CAS and ES can be determined by referring to the performance data section of the aircraft flight manual. Computing true airspeed ISD method to compute TAS using the ISD method on the doctor computer, solve, for each type of airspeed, in the order of I, C, E, and T, that is, change ES to CAS, change CAS to ES, and change ES to TAS. This process is illustrated by the following sample problem. Refer to definitions as necessary. Given, P equals 30.000, temperature equals minus 37 degrees Celsius, ES equals 253 knots, flight manual correction factor equals 2 knots, find, CAS, ES and TAS. CAS is determined by algebraically adding to ES the correction factor taken from the chart in the flight manual. This correction is insignificant at low speeds but can be higher than 10 knots near Mach 1. To correct CAS to ES, use the chart on the slide of the computer entitled F correction factors for TAS. Figure 322, enter the chart with CAS and PA. The F factor is 0.96. Multiply CAS by 0.96 or take 96% of 255 knots. To do this, place 255 knots on the inner scale under the 10 index on the outer scale. Locate 96 on the outer scale and read ES on the inner scale, 245 knots. Now, we need to correct ES for temperature and altitude to get TAS. As shown in figure 322, in the window marked for airspeed and density altitude computations, place temperature over PA. Locate the ES of 245 knots on the inner scale and read TAS on the outer scale. The TAS is 408 knots. Alternate TAS method. There's an alternate method of finding TAS when given CAS. The instructions for alternate solution are printed on the computer directly below the F factor table. Multiply F factor by TAS obtained with computer to obtain TAS corrected for compressibility. Mathematically, the answer should be the same regardless of the procedure being used, but the ISD method is used most often because the computation can be worked backwards from TOS. If the desire is to maintain a constant TOS, determine what is to fly by working the ISD method in reverse, also known as reverse ISD. Figure 323, Mach meters indicate the ratio of aircraft speed to the speed of sound at any particular altitude and temperature during flight. It is often necessary to convert TOS to a Mach number or vice versa. Instructions are clearly written on the computer in the center portion of the circular slide rule. Locate the window marked for airspeed and density altitude computations and rotate the disk until the window points to the top of the computer, toward the L0 index on the outer scale. Within the window is an arrow entitled Mach No. Index. Figure 324, to obtain TOS from a given Mach number, set air temperature over the Mach No. Index and, opposite the Mach number on the minutes scale, read the TOS on the outer scale. Example, if you are planning to maintain Mach 1.2 on a cross-country flight, place the air temperature at flight altitude over the Mach No. Index. Read the TOS on the outer scale opposite 1.2 on the inner scale. If the temperature is minus 20 degrees Celsius, the TOS is 742 knots. Airspeed indicators. The combined airspeed Mach indicator, shown in Figure 325, is usually found in high-performance aircraft or where instrument panel space is limited. It simultaneously displays EAS, indicated Mach number, and maximum allowable airspeed. It contains a differential pressure diaphragm and two aneroid cells. The diaphragm drives the airspeed Mach pointer. One aneroid cell rotates the Mach scale, permitting EAS and Mach number to be read simultaneously. The second aneroid cell drives the maximum allowable airspeed pointer. This pointer is preset to the aircraft's maximum EAS. Unlike the maximum EAS and unlike the maximum allowable airspeed, Mach number increases with altitude. An airspeed marker set knob positions a movable airspeed marker. This marker serves as a memory reference for desired airspeed. Air data computer. The air data computer is an electro-pneumatic unit that uses pitot and static pressures and total air temperature to compute outputs for various systems. These output parameters of voltage and resistance represent functions of altitude, Mach number, TOS, computed airspeed, and static air temperature. Air data computer outputs are used with the flight director computers, automatic flight controls, cabin pressurization equipment, and normal basic indicators. The air data computer provides extreme accuracy and increased reliability. Doppler radar provides the navigator with continuous, instantaneous, and accurate readings of ground speed Gs, and drift angle in all weather conditions, both over land and water. It does this automatically with equipment that is of practical size and weight. Its operation makes use of the Doppler effect. Two basic Doppler radar systems exist, the 4-beam and the 3-beam. Both types use either continuous wave, CW, or pulse wave, PW, transmission. CW transmission requires one antenna for transmission and a second antenna for reception. Both systems use an X-shaped beam configuration. Ground speed is computed by comparing Doppler shift between front and rear beams, and drift angle is computed by comparing the shift between the left and right beams. Doppler is not the only source of drift angle in Gs. The same basic information is available on virtually all inertial navigation systems, INS, and now Global Positioning System, GPS. Computers can also give accurate information under a wider range of conditions. Chapter summary. While the operation of some of the equipment in this chapter seems crude and primitive compared to state-of-the-art navigation computers currently in use, these instruments still have two very important uses. They act as cross-checks to ensure the computers are functioning properly, and they become your primary means of navigation when the computers are not.